Ain't gonna help much. So where we left off last day, to solve force problems. We are going to be approaching most force problems this year with a free body diagram. My abbreviation is FBD. We're going to draw one arrow for each force that acts on the object. Now listen closely, because this is a common mistake. Never put the net force on your diagram. Let me show you what I mean. What was the net force for this diagram here? What was the answer? What do we say the net force was? Read it to me, John. Do you see a 5 anywhere on the diagram? There's a reason for that. It doesn't go on the diagram. What was the net force here? 3.7. Does it show up on the diagram? It does not. All you're doing is you're putting your individual component forces on a free body diagram. The net force is going to show up in the equation. That's going to be really important because later on we get into more complicated stuff. Oh, you're going to want to put the net force because you're going to know the net force as an answer. And I'm going to be saying, find one of the component forces. And Jake, you're going to want to put it on your diagram. But as soon as you do that, suddenly you've introduced an extra vector that you're going to be freaking out on, trying to figure out what the heck to do with it. No, you didn't need to. Okay? So never put F net on a free body diagram. Label all the arrows. Put the tail of each arrow at the center of the object, if at all possible. Sometimes it's going to be so crowded, you'll have to move one a little bit over to make it readable. Acceleration and velocity vectors should be drawn differently from force vectors. From force vectors. I almost never put acceleration and velocity vectors on a free body diagram, but if I do, I might use a squiggly line or a dotted line to distinguish them from my force vectors. Use a free body diagram to write an algebraic net force equation, as in example 4F, and then solve for any unknowns. In fact, here's what we're going to be doing. Sydney, this year, we're often going to have stuff moving up and moving down in the same diagram. And so letting up always be positive and down always be negative, like we did last unit, is going to be counterproductive and confusing. So in this unit, we're often just going to say, look, who's winning? Which way is this accelerating? That's positive. Anything else is negative, except we're not actually going to put the negatives into the actual numbers, so we're not going to put in, Terry, a negative 9.8 anymore in this unit. Instead, what we're going to use is a tug-of-war analogy. We're going to always ask ourselves, who's winning? And then we're going to use this little equation here. Winner minus loser gives you your net force, where your net force is ma, where it's actually m, the net acceleration, but we get kind of sloppy. This allows us to avoid having to decide which directions are positive and which directions are negative. It actually, by asking this question, Dorothy, will give us always the most convenient one to use, trust me. And you can almost always visualize who is winning if you put your brain to it a little bit, especially now that you've done a year of physics. As an example, example 5. A 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. Draw a free body diagram. Okay. I represent the rock with a dot. And I'm going to try and give you a strategy that I think works for me when it comes to a free body diagram. So I'm going to say to you, Terry, something like this. What are the forces acting on this object? Get the obvious ones. I'm always going to say that right away because kids want to get the most complicated ones first. I'm going to tell you, get the obvious ones, and that'll help you get the more complicated ones, and it'll give you a system. So what are the forces acting on this rock? Get the obvious ones. And your response, unless we're in outer space, is always going to be gravity. By the way, when we get to orbit and outer space, it's going to be, get the obvious ones, and someone's going to say from the back of the room, not gravity. And I'm, yeah, it's not this time, because we're in outer space. Very cool. Gravity. FG. And also because I know what direction gravity acts, downwards. Is this object in free fall? Read the question carefully. Is this object in free fall? No, then there has to be another force acting. That's Newton's first. In the opposite direction. So which way is this force, which way is this rock accelerating? Jake, read the question carefully. Which way is it accelerating? Upwards. So the upwards force has to be winning. So I'm going to draw an exaggerated longer arrow to make sure that I know that's the winner. What did we call that for? What force is causing this rock, or this weight, this mass, to move upwards? It's a rope. We called that tension. Actually, you know, I'm remembering, I think I often use the letter T for tension, don't I? So I'm going to call it T for tension. Whatever, FT or T. Suddenly I'm remembering, I think in my answer keys, I almost always, did I use the letter T last year? I did. Okay. Who did you say was winning? By the way, A, free body diagram, done. And B says compare the forces. We did that in our free body diagram by drawing one arrow longer. So done. Who's winning, Jake? What do we call it, Jake? Okay. So my equation's going to look like this. Winner minus, now anything else that's pointing up, I would put a plus sign in front of, and that's going to, when we get into more complicated diagrams, be the case. Anything that's pointing down is going to be a loser, negative. So it's going to be winner minus FG equals F net. There's my equation. C. D says find the tension. Okay. How would I get the tension by itself, John, when you're done yawning?
Minus.
No. How would I get the tension by itself? Why would I plus the FG over, John? Because what's in front of it? You awake now? You good? Okay. So you're saying that tension is going to be, you're saying I can plus this over to that side. Now, what did I say F net was? That's really just MA plus, and what was FG last year all the time? MG. Let's walk through this right-hand side and see if we know everything. Do I know G? 9.8, not negative. We took care of the negative in our winner minus loser. No more negative in this unit. Do I know the oh. They didn't give me the map. Wait a minute. What did we call mg last day? We said that was the weight. Remember that? They gave me the weight. I don't actually need to know m or g. I know what, when you multiplied mg together, you got as an answer, because they said this is 2,000, not kilograms, Jaron, but what unit did they put right here? Ah, that must mean it is an mg. Okay, so I'm going to go like this. Plus 2,000. That's kind of convenient. Do I know A, the acceleration? Oh, they told me that too. That's very convenient. Do I know the mass? Nope. Can I figure it out, Josh? How? And you know what I'm actually going to do, because I'm really lazy? I'm going to write 2,000 over 9.8 right in the equation, and I'll type that right into my calculator, and that way I don't have to worry about rounding off. My calculator will carry it to 50 or 6 figs or whatever your calculator carries it to. Hey, what's the tension? No, I don't think so. I'm pretty sure it's bigger than 2,000, because the gravity alone is 2,000 and it's accelerating up. It's got to be somewhere in the 2,000 pluses. 2,612.2, which is 5 sig figs. Can I go 2.61 times 10 to the third newtons? Okay. So the weight of the rock was 2,000 newtons. The tension was 2,600 newtons. Question for you. Number 6. Is it correct to say that if the rock in example 5 is moving upwards, then the string tension must always be greater than the weight of the rock? I see some nodding. I see some shaking their heads. True or false, and convince me. Paige, you're not playing. I got a little further in my block Bs, and she saw this last day with. So those of you that haven't seen this already. Yeah?
True, because we're the rope, right?
So John says true because and I'm glad John said true, because he did a very, very common misconception. It would be true if the question said this. Is it correct to say that if the rock in example 5 is accelerating upwards, then the string tension must always be greater than the weight of the rock? Does it say the word accelerating?
No.
What word does it say? So let's look at the possibilities. How could we be moving? We could be speeding up, but what else could we be doing? Traveling how? That'd still be speeding up, accelerating. What? Oh, Sebastian, speak forth, speak loud. What?
Constant.
If we were at a constant speed, what number would I put right there for the acceleration?
0.
Oh, so what would happen to this term? So what would the tension be? Exactly mg. Yes? And the fact that they said moving and not accelerating is the key word in this question. So I'm going to say, first of all, false. And I'm going to write constant speed. I'll draw a little arrow. A equals 0. Tension equals mg. Right? And that's a perfectly good explanation. And for my ESL students, almost no English, perfectly good explanation. I accept like that, no problem. Ooh, example 7. For a rock moving upwards, is it ever possible for the chord tension to be less than the weight of the rock? So now let's go back to this equation, think about various permutations. Can it ever be less than the weight of the rock? Yes or no, and convince me. I've just shown you that it can be equal to the weight of the rock. Yes? Can it be less than?
Can the acceleration be negative?
Ooh. Look. Behold the rock. Watch closely. Watch very closely. Watch the string. What happened to the string for a split second there? It was slack, it was loose. So if the string is slack and loose, could the tension possibly be the same as mg? I think that would be the tension was less than mg. How can it be less than? If you give this a big jerk, if you temporarily accelerate it upwards, like that. Saw it for a split second. Yeah. So, good catch. Yeah. If we yank the rope, so rock accelerates upwards for a split second, the rope will be slack. Guanting, Victoria, look up. Slack, when the rope is loose, we call that slack. Okay, new word for you. Oh, and if your grandparents use that word, it refers to a pair of pants, right? Put on your slacks, your grandparents oh, what a terrible word. My mom still uses that one all the time. Calvin, we're going to a funeral. Put on some nice slacks. I don't call those it. Does anyone use that word anymore? That is a 1950s word. Next page. Turn the page. A technical comment on force equations and vectors. Every so often, I'm going to have to get fussy and technical. Do you remember on the very, very first day, Gabby, you weren't here, but the rest of you, I told you almost everything I teach you this year is garbage. It is. We're simplifying like crazy. For example, this is garbage because there is another mass in this question that I totally ignored. Do you see it? Yeah, our rope has no mass. Oh, and that would be a tough question because if we actually have a pulley, the amount of rope that's hanging below the pulley is constantly changing. It's a constantly changing mass. That's where you need calculus. That's what calculus was invented for, if you have stuff that's constantly changing. So, technical comment here. If the mass of example 5 is accelerating down, say 2 meters per second squared, we have two choices. You could, if you want to, use the sign convention from last unit and say up is always positive, down is always negative, left is always negative, right is always positive. And we could write it this way. Tension minus mg equals a negative. you know what? I'm not a big fan of always letting down be negative. So I wrote down here, this first approach works very well for one-dimensional problems, but for many body problems where you have something moving to the right, which last unit was positive, and something else moving down, which last unit was negative, yeah, you know what? Let's just not worry about always having to the right be positive and down be negative, because that's going to get confusing. We're going to decide which way is it accelerating. That's the winning direction. That's the positive direction. Okay? Oh, I wrote down here tricycle demonstration, one of my favorite demonstrations. I have to pause the video, though. Homework questions you can do. I think you can now try safely number 1, number 2. 3 is good. So we're going to start to go abstract on you now in Physics 12 quite often. We'll say, hey, look, if force F moves an object with a mass m at A, what will force the same F move an object with mass half of m? What will A be? That kind of a thing. So this is your first experience on that. 4 is good. 5 is good. I think I gave 5 to my Physics 11s last year. They might remember it because it's so simple it's tough. 7 is good. 8 and 9. 9 is nice. Some rock climbing. Sounds like a lot. You'll get lots of time. So I think, I skipped what? 10 and I skipped 6. Skip 6, skip 10. There's an easy way to say it. Some nice applications.